Every single piece of electronic equipment out there relies on a concept that is universally taught, yet honestly, fundamentally misunderstood. I'm talking about the ground plane. Today, we're going to explore the physical reality of how current actually routes itself on a board. By the end of this explainer, you're going to master the practical intuition of trace routing, common impedance coupling, and the exact mathematics behind why high-frequency signals behave so strangely. Right. Let's start with a really simple question. Is ground actually an idealized 0 volts? See, textbook schematics love to treat ground as this infinite, magical 0-volt sink. Basically, a bottomless pit where currents just magically disappear. But, as you probably guessed, this couldn't be further from the truth. We are going to shatter that myth right now. The reality of electromagnetic compatibility, especially when you dive into Henry Ott's masterwork on the subject, demands that we look at physical laws, not just idealized symbols on a page. Okay, let's break this down by comparing two definitions. First, you've got the voltage definition, which calls ground an ideal equipotential plane. It's a nice, clean theory, but it totally ignores physical reality because, let's face it, no real-world plane has zero impedance. Instead, we absolutely must use the current definition. This defines a signal ground as a low impedance path for current to return to its source. I want you to picture this visual analogy. Think of current not as a drop of water falling into a bottomless well, but like a flowing river. That water absolutely must carve a physical, continuous path all the way back to its source. And because the current flows through materials with finite impedance, a difference in potential is always going to exist between any two physically separated ground points. Okay, moving into section 1, zooming in on low versus high frequency paths. To truly understand how this river of current carves its path, we need to look past the surface and zoom straight inside a double-sided printed circuit board. The core dichotomy of how current behaves in there hinges entirely on one thing: frequency. At low frequencies, the ground current takes the path of least resistance, but at high frequencies, the behavior flips completely. The current suddenly takes the path of least inductance. And here's the kicker. This flip doesn't happen at some crazy high gigahertz level. The threshold is typically just a few hundred kilohertz. Let's actually track this low-frequency return current. Notice how the current flows directly from point A to point B. It takes this wide, lazy loop because it is purely seeking the lowest resistance, which means the shortest physical distance straight across the copper plane. But remember, having a large loop area is highly undesirable. Why? Because it acts exactly like a giant antenna, picking up and radiating noise all over your board. At low frequencies, you often have to physically force the current to flow where you want it. Now, the high-frequency reality flips the script completely. Look at how the current tightens up right beneath the signal trace. It's exactly like a stretched rubber band suddenly snapping back into place directly under the wire. By flowing right under the signal trace, the current minimizes its loop area, and doing that directly minimizes the inductance. High-frequency ground currents actually do exactly what we want them to do naturally. They keep the loop small. So as designers, our only real job is to provide an uninterrupted plane so we don't accidentally block this natural path. Which brings us to section 2. The math of common impedance coupling. So what actually happens when multiple circuits are forced to share these ground returns? Well, we need to transition into the strict mathematical rules that dictate circuit interference, what we call common impedance coupling. Here is the exact mathematical expression derived in Ott's text. We have VL1, which equals VS1, plus ZG multiplied by the sum of I1 and I2. Let's break down exactly what this math is physically telling us about our layout. Breaking down these variables step by step. VL1 is the voltage across your load. VS1 is your source voltage. Now, the absolutely critical term here is ZG. That represents the common ground impedance. Notice how ZG is being multiplied by both I1, which is the current of our primary circuit, and I2, which is the current from a completely different circuit. So the crucial takeaway here is that the term I2 times ZG mathematically represents inner circuit noise. It physically proves that the current from circuit 2 is actively infecting the voltage of circuit 1, simply because they are sharing a ground path with a finite impedance. Now, how do we fix that impedance? We minimize the inductance. Let's focus on equation E-23, which calculates partial inductance. The formula is lnp2 equals mu L over 2 pi times the quantity of the natural log of 2L over R2 minus the natural log of 2L over D. I want you to look specifically at that variable D right there at the very end of the equation. D represents the physical distance between your signal conductor and your ground conductor. Because D is in the denominator of that second logarithmic term, which is being subtracted from the first term, making D smaller mathematically increases the value you are subtracting. Therefore, physically placing the ground and signal conductors closer together mathematically forces the total net inductance to drop. It's just this beautiful marriage of physical layout and pure mathematics. All right, Section 3, a practical walkthrough on shared ground returns. To really lock this in, let's look at a practical, real-world example of that shared ground relationship. If you track the bottom wire on this schematic down to the single return path marked ZG, you'll see what I mean. Imagine circuit 2 experiences a massive spike in current. Let's say it's a digital logic chip switching states really fast. That current, I2, rushes down right through ZG. Because ZG has resistance and inductance, a voltage drop instantly occurs across it. Now, circuit 1, perfectly innocent and just doing its own thing, suddenly finds its ground reference bouncing up and down entirely because of circuit 2's current. So if you are ever debugging a noisy board, you need to follow these exact methodical steps. First, visually identify the shared impedance path, that's your ZG, on your physical layout. Second, calculate the intra-circuit noise. That's simply your own signal's current multiplied by ZG. Third, and absolutely most importantly, isolate the inter-circuit noise by calculating the interfering circuit's current multiplied by ZG. This equation drastically simplifies the incredibly frustrating task of isolating circuit interference because it tells you exactly where to look, the shared copper path. Let's move to Section 4, the gotcha of grounding topologies. You see, understanding how ground currents want to flow is really only half the battle. How you physically lay out your grounding topology ultimately dictates your success. These dense engineering topologies can basically be distilled into 3 memorable categories: single-point grounds, multi-point grounds, and hybrid grounds. And trust me, each has a specific frequency domain where it shines and a domain where it will absolutely ruin your day. Let's look at a massive gotcha pitfall. This is a series single-point ground, commonly known as a daisy chain. Sure, it is extremely simple and cheap to wire, but it is fundamentally terrible for noise. Think of it like a bad traffic jam. Circuit 3's return current has to drive through Circuit 2's intersection and then through Circuit 1's intersection just to get back to the source. The impedance accumulates linearly, so the noise voltage at Circuit 1 ends up being a function of the sum of the currents from all 3 circuits. The actual solution for high-frequency designs is the multi-point ground system. Instead of daisy chaining, every single circuit drops straight down into a low-impedance ground plane. Connections are kept to a fraction of an inch just to minimize the inductor effect of the via itself. And here's the real kicker. From the text, at frequencies over 100 kilohertz, stray capacitance completely destroys single-point systems anyway. So a multi-point ground plane becomes absolutely mandatory to give those high-frequency currents that path of least inductance they are desperately seeking. Which brings us to our final section, the summary and core takeaways. We have transitioned all the way from idealized textbook theories down to the atomic realities of PCB layouts. Let's lock in the absolute most critical concepts here. First, never forget that ground is a return path for a flowing river of current. It is practically never an infinite 0-volt sink. Second, behavior completely flips at high frequency. Current acts exactly like a snapping rubber band, mimicking the trace above it to find the path of least inductance. And third, physical proximity is your best mathematical weapon. Moving the return path physically closer to the signal mathematically lowers the total net inductance of your circuit. I want to leave you with this rather dramatic mic drop quote from Terrell and Keenan that's referenced in our text. "Thou shalt have but one ground before thee." If you treat your ground return paths with the exact same respect and care as your most sensitive signal traces, your circuits will work flawlessly. So the next time you drop a via onto a board, ask yourself, are you building a solid foundation or are you building a trap for your own signals? If you found this breakdown valuable, make sure to hit subscribe for more EMC engineering and hardware survival guides. Until next time, keep routing smart.